the purpose of this lecture is to give a rigorous proof of the Cauchy theorem. So let me recall what the Cauchy theorem says. We have a domain, omega, which is simply connected, and we have an analytic function f in this domain. And then the Cauchy theorem says that if we integrate f along any closed contour, then we will get 0. So the Cauchy theorem is really the basis for everything in the theory of analytic functions. From this we can deduce the Cauchy integral formula and power series expansion and infinite differentiability and all that. So we really should have a rigorous proof of it. Earlier in the course I have motivated the Cauchy theorem from the green formula. But that's not really an ideal solution. First of all, we do not really prove the green formula in a very rigorous way in earlier courses. And even if we did, it turns out that the green formula needs more regularity than is really necessary for the Cauchy theorem. So in this lecture, I will give a proof of this, which does not really demand anything from f except that it's complex differentiable then. Okay, so let me start by noting a situation where the Cauchy theorem is, so to speak, obvious. It's the case when we can find a primitive function. If given this function f, we can find capital F such that the derivative of capital F is f, then the Cauchy theorem is sort of obviously true. It's really the fundamental theorem of calculus, you might say. Because if you integrate f now along a contour, you can evaluate this using capital F. This will really be equal to the difference between the values of capital F at the end point and the start point. And if the contour is closed, then these values will be equal and the integral will be 0. However, you cannot really use this as to prove Cauchy theorem because you don't really know from the beginning that a given analytic function has a primitive. So we have to do it in some other way. But we can still note that there are some simple cases which will be very useful where you can apply this argument. For example, if you integrate the constant function 1 over a closed contour, or if you integrate the function z over a closed contour, then in both cases this will give you 0. And the reason is that it's so easy to find primitive functions here. Here the primitive function is just z, and here it's z squared divided by 2. Actually, we will only use this fact when the curve gamma is a triangle, and then it's actually possible to write down explicitly what these integrals will be, and you don't even need the fundamental theorem of calculus. Okay, so let me then start this proof by a special case. So I formulate the Cauchy integral theorem for a triangle. So suppose that T instead is a triangle. And F is analytic in a neighborhood of the triangle T. Well, then the integral of f of z dz over the boundary of the triangle will be equal to 0. So this, you might say, is the Cauchy theorem for a triangle. So before we go on, let me introduce some notation here now. So if P is any triangle, in the following, I of P will just mean the integral of the given function f of z over the boundary of this triangle P. So what's the idea in this proof now? Well, let's start by considering an arbitrary triangle here now. And so the idea is that we should use a kind of subdivision procedure here. So we will divide this triangle into 4 congruent subtriangles. So if the original triangle was T, then let's call these triangles T1, T2, T3, and T4. And then we make the observation now that if you integrate around the boundary of T, by the way, all integrations in the following here now will be in the positive direction. Then this is actually equal to the integral, the sum of the integrals along all these subtriangles, the boundaries of these subtriangles. So why is that? Well, if we integrate along this triangle like this, and then along this triangle, and then along this triangle, and then along this triangle like this, then we see that for every inner boundary here now, we will get 2 contributions, the integral from there to there, and the integral from there to there, for example. And this means that all these contributions from the inner edges, so to speak, they will cancel out. And what's left then, when you add the integrals over these 4 triangles, is just the integration around the outer boundary, which is exactly what we have on the left-hand side. Okay, so this is the first observation, and then we apply the triangle inequality to conclude that the absolute value of this I of t must be less than or equal to the sum of the absolute values of these terms here now. Like that. And from this, we can now conclude that at least one of these 4 triangles, T1, T2, T3, or T4, must have the property that the absolute value of the integral around the boundary is at least 1/4 of this value then. So we choose this one, or one of those triangles with this property. We call it T1, with a 1 up here now to mark the difference from that T1. And so what the conclusion is that the I of this triangle T1, absolute value, is then larger than or equal to 1/4 of the absolute value of I of t, like that. So let's suppose that it was T2 which was it had this property then. So how do we go on then? Well, then in the next step we subdivide this triangle into 4 congruent subtriangles like this, and repeat the procedure. And the conclusion is then that we can choose one of these 4 triangles. Let's call it T2 then, like this, and conclude that I of T2, absolute value, must be larger than or equal to 1/4 of the absolute value of I of T1, which then, of course, by the previous inequality is larger than or equal to 1/4 square times absolute value of I of t, like this. Okay, so if we now continue this subdivision procedure, then what we get is a decreasing sequence of triangles like this. This sequence has the property that if we integrate along the boundary of tk, takes the absolute value, then this will be larger than or equal to 1 over 4 to the power k times absolute value of I of t, like this. And now we note that the intersection of all these triangles, you can write it like this, will just consist of 1 point. Well, actually, since this is a decreasing sequence of compact sets, we know from advanced calculus that the intersection will be non-empty. And since the diameters of these triangles will go to 0, obviously the intersection cannot contain more than 1 point. So let's call that point Z0. Actually, to introduce some terminology now, let D be the diameter of the triangle T, and dk will be the diameter of tk. And then we note now that obviously every time we make a subdivision, then all the triangles in the subdivision will have half the diameter of the previous one. The diameter is, of course, just the maximal distance between 2 points in the triangle, which in the case of a triangle, obviously, is equal to the length of the longest side. So from this, we easily see then that the diameter of tk will be the d divided by 2 to the power k. And let's also denote by p the perimeter of the triangle. That is the sum of the lengths of the sides in the triangle. And similarly, pk will be the perimeter of tk. And again, when you make this subdivision, it's obvious that the perimeter of any triangle in the subdivision will be exactly half the perimeter of the triangle that you subdivide. So you get a similar formula here now for pk, which is then equal to p divided by 2 to the power k. Okay, so let us now choose an epsilon larger than 0. In the end, epsilon will tend to 0 then, of course. And then what we will do now is to use the fact that the function f is analytic at every point, thus in particular at the point Z0 here now. So what does that mean? Well, in particular, it means that given epsilon strictly larger than 0, we can find delta strictly larger than 0, so that the following is true. That the differential quotient here now, and then minus f prime of Z0 absolute value. So this is less than epsilon for absolute value of Z minus Z0 less than delta. That's really the definition of differentiability at the point Z0, which implies this. For our purposes, it's, however, slightly more convenient to rewrite this by multiplying by the denominator here. So we get an alternative version here now, which will be fz minus fz0 minus f prime of Z0 times Z minus Z0 and then absolute value of all this, is less than epsilon times the absolute value of z minus z naught. Again, for z minus z naught absolute less than delta then. So this is the observation then. And let us now choose k so large that dk is less than delta. Remember, dk was given by this expression, which obviously tends to 0. So of course you can choose k so large that this will become less than that. And then we now consider the integral over the boundary of tk, which by definition then is equal to the integral over boundary of tk of f of z dz. But now we use the first observation we made in the beginning, that we already have the Cauchy integral theorem for a constant and for the function z. We already know that if we integrate the constant 1 or the function z around the boundary of a triangle, then we'll get 0. Which means then that from this function f here, we can subtract any constant and linear function. In particular, we can subtract this expression. So this will then obviously be equal to the integral of f of z minus f of z naught minus f prime of z naught times z minus z naught dz. Yes, and then we take the absolute values here now. So we absolute value of this I of tk is equal then to the absolute value of this integral, which in turn is equal to the absolute value of this integral. And now we know how to estimate a contour integral like that. We know that this can be estimated, the absolute value of the contour integral can be estimated by the supremum of the integrand, or the absolute value of the integrand here now, times the length of the contour. So this will give us now supremum of, for z on the boundary of tk here now, of f of z minus f of z naught minus f prime z naught times z minus z naught end of absolute value, and then times the length of the contour here now, which is the perimeter of this triangle tk. And so how can we estimate this now? Well, remember that this expression is exactly the one we have here. And if z naught is a point in the triangle tk and z lies on the boundary, then obviously the distance between these points is less than the diameter. So we can apply this inequality here now. And then this will give us that this expression is less than epsilon times, well, we have here absolute value of z minus z naught, but that's of course less than the diameter of the triangle. So we get dk here, and then times the perimeter of the triangle, which was then pk. And if we now come back to our formulas here, we see that this can be written then as epsilon times d divided by 2 to the power k times p divided by the 2 to the power k, which is then epsilon times d times p divided by 4 to the power k. So let us see what we have achieved here now. On the one hand, we have estimated the integral here now, I of tk, absolute value then, by this expression. So it's less than epsilon times d times p divided by 4 to the power k. On the other hand, for what we did previously here, we see that we have an estimate from below of this expression, which is then 1 over 4 to the power k times absolute value of I of t. And if we now simply forget about what's here in the middle and now take this inequality and multiply by 4 to the power k, then what we obtain is that absolute value of I of t here is less than epsilon times d p, yes, like this. And now, since epsilon is arbitrary, we can choose epsilon as small as we like, which implies that this number must be 0 then, which is actually the theorem that we wanted to prove. So let us now turn to the general Cauchy theorem. And for this, we need the following concept, the concept of a null homotopy. So consider a closed contour in this domain omega. So here is the closed contour then. And then we say that that gamma is null homotopic if there exists a continuous map h from this unit square in the plane into omega with the following properties then. First of all, for the first variable here in h equal to 1, we should get a parameterization of the contour here. Secondly, when you put the first variable equal to 0, then this will just be a constant, some point, say z0 here then. And thirdly, for every value of the first variable, you should get the same image if you take 0 or 1 here. So this is really the mathematical description of a continuous deformation of the contour gamma. So you can think of the first variable in this function of the variable s and t. You can think of the first variable as a parameter, and so what you really have is a parameterized family of closed contours here. And for s equal to 1, you have the contour gamma. For s equal to 0, and you have just this point. And in between here, you get contours which sort of shrink down to this point when s approaches 0 then. And this third condition guarantees that all the contours that you get on the way, they're actually closed contours then. And using this concept, we can now write down the general Cauchy theorem, one version of it. We can say that if f is analytic in this domain omega, and gamma is a closed null homotopic contour in omega, then the integral of f of z dz over gamma is equal to 0. So we might say that this is a slightly more general version of the Cauchy theorem than the one I stated in the beginning. But that version actually immediately follows from this one, because if we suppose that the domain is simply connected, as we did, then you see by the definition of simple connected, then every closed contour is null homotopic, and then hence every integral along a closed contour will be 0 then. So this is really what we want to prove. And the idea behind this proof is now that what we really want to do is to, so to speak, split the interior of this contour up into triangles like this, and so on. And then we want to integrate around each triangle and use the first theorem that we proved to deduce that every such triangle, every such integral will be 0. And then if we add all these integrals around all these triangles, then by the usual argument in vector analysis, all contributions from inner boundaries here will cancel out, and we will be left with this, the integral around the original contour here, which will then also be 0. And this is actually what we will do. But there is a slight technical problem here now, because you cannot, if you have a general contour like this, you cannot really expect to be able to divide the interior up into strict triangles, because then the contour itself would have to be piecewise linear, and in general it's not then. So this is the first technical problem that we will have to deal with. And this is done by the following proposition then. So let epsilon be a positive number then. And then suppose let gamma epsilon be piecewise linear contour which is epsilon close to this contour gamma in the following sense. Well, first of all, a piecewise linear contour, it has edges and it has corners then. And the corners of gamma epsilon all lie on gamma. So if you have this contour here now, well, let me write draw a contour here, then all the corners of the, so to speak, approximating contour gamma epsilon will lie on the contour itself, so it will look something like this then. That's the first condition. And the second condition is that the maximal length of the line segments then in gamma epsilon is less than epsilon. So suppose that we for every epsilon have every epsilon strictly larger than 0, we have a piecewise linear contour of this type then, which you can think of as approximating the original contour then. Then the conclusion is then that if you take the limit of when epsilon tends to 0 of the integral of f of z dz over gamma epsilon, then this will be equal to the integral of f over gamma. So this is really a technical lemma. However, if you make the right definition of a contour integral, it's actually a trivial lemma. The right definition means that you should not start with defining the contour integral by parametrization, but you should start with the curve itself then and work with Riemann sums. And then this is actually essentially the definition of this this contour integral, you might say. This is in the textbook Saf-Schneider then. So what we need from this proposition is just the observation that if we can prove that the integral of all these integrals over these approximating contours gamma epsilon, all these are 0, then of course this will also be 0 then. So what remains to be done to prove the general Cauchy theorem is now to construct a sequence of approximating contours, which we call gamma epsilon then, for which we actually can triangulate the interior and prove the Cauchy theorem. And so how should we construct this sequence, and how should we prove the Cauchy theorem? Well, the only thing which we really have to work with is this homotopy map H. So let me start by sorting out a few topological questions about this. H goes from this square now in the this unit square in R2 into omega here. And H is continuous. And let us then consider the set K, which is the image under H of the unit square. So the first observation we make is that this is a compact subset of omega. It's not necessarily true that this compact will lie inside the contour. But what is true is that it lies strictly inside omega by definition. And then we can conclude from topology or advanced calculus then that the distance from K to the complement of omega will be strictly positive. This is a number which we call epsilon 0, and it's strictly positive. So the image under K may very well go outside here now, but it cannot get too close to the boundary here. And in the following now, we will construct these approximating contours gamma epsilon for epsilon between 0 and epsilon naught. And to do this, we also need uniform continuity. So it's again a theorem from advanced calculus that if you have a continuous map on a compact set, then it's uniformly continuous. And in the following, and in this situation, it means that given this epsilon now, we can find delta strictly positive then, so that if we take 2 points in the square here, which we can call S t and S prime t prime, and take the distance between these 2 points. And assume that that distance is less than delta, then this should imply that the distance between the image point under H is less than epsilon. For every epsilon you can find a delta such that this implication is true, and this is really the content of the concept of uniform continuity then. So what we will do now is to subdivide this square into small triangles, like this, something. And we make all these triangles here so small that the diameter of each triangle is less than delta. And in a sense, we would like to use the images of these triangles to triangulate the interior of this contour here. But we cannot really do that because this is only a continuous map, and the image of a triangle under a continuous map is not really a triangle, and it's actually not even, you cannot even be sure that you can integrate along the boundary. So what we'll actually do is to consider the set of all these triangles here with diameter less than delta, and to each triangle SK we associate a triangle over here which we'll call TK, which we form in the following way, that we take if this is SK, say, then we take the 3 corners of SK, map them by H, and then take the triangle with these three points as the three image points as corners. Then we get triangles over here, and we consider the set of all these triangles then. So one should observe that this map can look very strange. It's not at all necessarily bijective. So these triangles may lie on top of each other and so on, and they can degenerate into lines or points even. But still, nothing of this will affect the argument which I'll come to now. So the only point which is necessary to observe now is that all these triangles actually lie strictly inside omega. Why is that? Well, because the corners of the corresponding triangle over here, SK, lie, the distance between corners in SK is as most delta. So by this uniform continuity property, the corners of the corresponding TK can have a distance which is will have a distance which is less than epsilon then. And since the corners obviously lie in K, because I mean by definition they belong to the image under H then, and since epsilon is less than epsilon 0, then of course every point in TK will lie closer than epsilon 0, k, and hence strictly inside omega then. So here I have drawn a map with the triangulation, of the unit square. It looks something like this. So this edge here now is mapped onto the point which I called Z naught before here. And this edge is the one which corresponds to S equal to 1, which is actually mapped onto the contour, the contour gamma really looks like this, but this will be then the approximating contour gamma epsilon here. So in this case, of course, I've only divided into each side into 5 pieces, which doesn't give a very good approximation, but just as an illustration then. So these two edges here now, they will both map onto this curve here now. Okay, so for example, here I have one triangle, and you can see that it will map by this map onto this triangle here then. So this is how it looks then. And how do we now prove the Cauchy theorem, and how do we construct gamma epsilon? As I said, gamma epsilon will simply be the contour which has corners at this point, E1, E0, E1, E2, E3, E4, E5. So it will be this piecewise linear curve. And by construction, the distance between the length of each of these edges here will be less than epsilon then. And all the points lie on the original gamma then. So let us now consider all these triangles here now, TK. And we integrate along the boundary of each one of them. F of Z dz. And then we sum over K. And then, obviously, by the previous simple triangular version of the Cauchy theorem, each term is 0 here now. So the sum is also 0. But now I also claim that this is equal to the integral of f of z dz over gamma epsilon, that is over this piecewise linear contour. So why is that? Well, again, it's the usual argument in vector analysis. If we take any inner edge here in the picture, for example, this one, then it's obviously the edge of two triangles here. And when you integrate around all the triangles, you will get one contribution when you integrate in this direction and one contribution when you integrate in this direction, and they will cancel out, So the inner edges does not at all contribute to this sum. Then you also have edges like this one and this one. But they both map onto the same segment here now. So, and they will be transversed in opposite directions here now. Here if you go here in this way and here in this way, you will get one contribution in this direction and one contribution in that direction. So they also cancel out. All these edges here, they map onto the point Z0 in the middle here. And so the integral over these points does not contribute anything to the sum either. So the only thing that is really remains in this sum after this operation is the sum of the integrals over the outer edges, that is along the edges corresponding to this curve, which is exactly gamma epsilon. So now we see that the integral over gamma epsilon is 0. And that is really, by the previous argument, all we need to prove the Cauchy theorem in general.